Now if I ask you straight away how much heat energy it would take to get ice water, so 0 degrees Celsius, to the boiling point, 100 degrees Celsius, you say, well, it's going to be 100 degrees Celsius change in temperature. What you would not be able to do right now is tell me how many joules of energy that's going to take, or how many calories. Because what we haven't talked about yet is the conversion factor between energy and temperature. Now, let's take a couple of observations to set the stage for that. Now, different materials are going to be harder to warm up than others. If on a cool day you've sat down on a piece of stone or on a wood bench, you've noticed that the stone felt a lot colder than the wood when you sat down. But aren't they sitting out in the same temperature? Absolutely, as long as they're both sitting in the same shaded place so we don't have the sun warming them up or something, right? So why do they feel so much different? Or, using another example, if you reach into your kitchen cabinet and you grab a Tupperware container out, made of plastic, and you grab a pan, the pan feels cold. Tupperware doesn't. But they're both sitting in a room that's been kept at probably somewhere around 72 to 73 degrees Fahrenheit. That's what we usually aim for. Or in the low 20s Celsius. They're the same temperature, so why do they feel different? Simply put, what you feel is the heat flowing out of your hand and into the material. And because some materials take more heat energy in order to warm up, they feel colder. You feel that more heat flow out of your skin. Now that tells us that there's going to be something important about different materials that requires a different amount of heat energy to create a temperature change. And we'll have to account for that material by material. Now, also we've noticed that more massive materials are harder to warm up. Proof of that one, if you take a saucepan filled with water that's this deep versus one that's filled this deep, this one boils first. Why? It takes less total heat energy flowing in to raise that water's temperature up to the boiling point. When you have more water, it took more energy, and that meant you had to let it sit on the burner for longer to accumulate that energy and raise the temperature. So there's two different things that we need to consider so far when we talk about converting from heat energy into temperature. We need to consider the material and also the mass of that material. And we're going to have both of those involved in any of these conversions where we're going from heat energy into temperature. Now, let's just make sure that we get that nice and concrete. If I take 1 gram of steel and I raise it 1 degree Celsius, and I take 1 gram of water and I raise it 1 degree Celsius, here's how much energy we need to use in each of those. It turns out I have to use much less heat energy to raise the temperature of steel than it does to take up 1 gram of water by that 1 degree Celsius. Well, why? Well, it's not the density to focus on so much, and you might start thinking about that since 1 gram of steel is taking up way less space than the water. That might have a little bit of correlation, but it's not what we're talking about here at all. The key thing is that the steel heats up faster, or heats up more easily is probably a better way to say it. It takes less energy to heat up 1 gram of steel. For water, we have to add almost 10 times more energy to raise the temperature just as quickly. Now I'll point out a neat outcome of that too. If you've got your pot of water, the metal here is probably going to be fairly uniform in temperature, even though only the bottom is in contact with the burner. The water is also going to be somewhat uniform in temperature. You know, you've got those eddy currents helping it mix. If you're stirring it constantly with your spoon or whatever, it will be pretty homogeneous for its temperature. But the temperature of the water is going to start out much lower than the quick rise in temperature you get for the metal. Slowly the water is going to be heating up. How much more slowly? Well, as slow as it takes to get 10 times more energy to transfer into the water, right? So that's one of the things you've observed. Now let's go ahead and handle that in terms of the equations that we need and the mathematics for it. For that, look at the video on heat capacities.